Hi, I'm Philip White. This is my second YouTube video that I'm making to demonstrate some of my professional skills and expertise. In this case, my video is geared more towards experienced programmers than my previous video on JavaScript was. In this video, I'll walk you through how to use resource management in C++ to be as efficient as possible. There are two major types of resources that computers consume: space and time. This lecture will show how to manage uses of these resources to create software that runs quickly and without taking up too much space and memory. In some cases, a program will be run lots and lots of times within a broader program. In that case, if you are running, say, the same algorithm 20,000 times in a row, you will really want to minimize the number of milliseconds that your code will take to run. I chose the example that I'm going to use today, simulating very simple circuits, ones that have NOT gates and that have wires on binary strings in C++. Only NOT gates. Circuits that have only NOT gates, based on my experience working on an innovative startup idea that I'm working on that's related to neural networks. While studying neural networks and how to write code about them, I learned some valuable lessons about both memory management and computational complexity and speed. I'm going to share those lessons with you today. In this video, the sections that I'll cover are possible and less efficient ways of representing tree structures, including circuits, with pointers and linked lists, the running times of algorithms, an alternate way to represent circuits using vectors, defining the gate class with vectors and the bool data type to have just two possible values for the circuit gate ID, using what I call rolling computation to run on one row and then the next without saving more than two rows of circuit gates in memory at the same time. And this is done by using a simple while loop instead of crawling a tree. Using out-of-the-blue curly brackets to deallocate memory quickly during a computation where memory could be freed, and using parallel processing to allow the individual processing of one row at a time to be done in parallel. I'll post a little bit of source code on the screen. Let's get started. One thing I should mention is that for the sake of demonstration, I decided not to use any for loops. You may not know this even if you are a veteran C++ programmer, but one use of for loops in C++ is that they are a convenient way to deal with deleting variables from memory when they are no longer being used. When you write a classic int I equals 0 declaration in a for loop, the variable is deleted at the end of the for loop. Here I'll show you how to do the same thing with just while loops. Here is the typical way to define a tree on the screen using techniques related to doubly linked lists. As you can see, this way of describing a tree node using pointers and a sort of recursive definition, the struct circuit gate here is one where there's an ID, which corresponds to one element of our set of logic gates, which here includes exactly one element, the NOT gate. And since the circuit gate class is currently being defined, meaning that we can't use its definition directly in the struct, we use a pointer to an address in memory to a circuit gate instance, so that we can access our definition of circuit gate within itself without requiring that the struct be fully defined before we refer to it. You'll note that you cannot include a circuit gate element without the asterisk included in C++. One problem with pointers is they are hard to work with, confusing to some developers, and dangerous in the sense that if, for example, you declare a pointer and forget to delete it, you could mess up memory management on a computer's hard drive. Additionally, building out a whole connected tree of nodes that are circuit gates would be inefficient. The running time of algorithms is very important. As I said previously, sometimes algorithms have to be run thousands or even millions of times, meaning that in some cases, every millisecond counts. There is a well-known concept in computer science called Big O notation, which allows for a clean, precise mathematical representation of the speeds of algorithms. In this video, we're going to explore alternate source code ideas for how to represent circuits. Specifically, we're going to use vectors and, while we'll have one master vector of gates that captures the totality of the circuit for input, storage, and reference purposes, we will, when computing on the circuit, avoid using excess memory by utilizing vectors that we will quickly delete after each use. Here on your screen, you should see some source code and Xcode that represents circuits using vectors. Instead of using a tree, we can hop from one vector to another and avoid storing the entire circuit represented as a tree with parent and child nodes again in memory. You'll note that we have defined the gate class efficiently, the gate struct efficiently, same idea, with just one Boolean variable that we can set to true or false to capture all two possibilities for what a particular gate object can be, a NOT gate or no gate at all, where the latter of those two does not change an input bit that is passed to it. Ultimately, we're going to use a function that will include two for loops. One, a for loop to process all of the rows one by one, and a second for loop, which we will parallelize to compute each row of gates faster, inputting the input bits from the previous row's output and outputting bits for the next row of circuit gates to process. Finally, for the sake of demonstration, we're going to use a variable scope trick where we insert curly brackets around a variable with the left bracket coming right before the variable is declared and the right bracket occurring precisely when we want to delete that variable and release its allocation of memory. You will see how that was implemented now. Here is the code for everything that we're going to do. In a moment, I will run the code once, and as you may have noticed, I have included a functionality in the program that will measure how many milliseconds the program takes to run. I will also run the code 2 million times to verify that it runs fast enough that it won't take too long. When I compile this program, I will not use optimization to avoid eliminating redundant code that doesn't change the input. I want to measure how long it takes. It runs very quickly when it is repeated once. I ran it for 20,000 steps by including a for loop right before the first curly bracket that I included for memory deletion. It took less than a second. I then ran it for 200,000 steps, and it ran for less than 3 seconds. Let's check it out now. As you can see, this program runs very quickly. If you run the code without the parallelization for 2 million cycles, it takes 1 second longer to finish, 23 seconds instead of 22 seconds. In C++, every second counts. Anyway, we have achieved our objectives and done everything that we could to speed up this simple program. I hope you understand how the techniques I presented, which include parallelization, complexity-focused, object-oriented design, and memory management with code blocks and variable scope, can help professional coders to write efficient code that allows developed and released software to run smoothly and efficiently. No one really wants to wait 5 minutes for a web page to load. With these tools and some others, including algorithm design, it is generally possible for good developers to avoid that outcome. Thanks for watching my video. Bye.